Hey guys, I apologize for the last video that got cut off, but we're going to go ahead and pick up right where we left off on those QF2 notes. So we left off on QF2, looking at problem 1, finding the X and the Y-intercepts here on problem number 1. So we found the Y-intercept, we found the X-intercepts. There are two of them there, X equals 0 and X equals negative 1/3. We can also check that by taking a look at a graphing calculator. And here I have the graph for 9x squared plus 3x. And I can look and see there that I have x-intercepts. This would be approximately negative 1/3. And this is 0 for my x-intercepts. Now I can also see my y-intercept is 0 there as well. So we do have the correct x-intercept and the correct y-intercept here for h of x. Let's go ahead and move on and take a look at problem 1c. So as I take a look at 1c here, I want to find the y-intercept and the x-intercepts if they exist. So finding the y-intercept again, we can find this very quickly, very easily. We know that the y-intercept can be found by setting the x values equal to 0. Or in this case, or in all cases, that would just be the constant at the end. So the y-intercept is going to be 9. So we know that right away, just the constant at the end. The x-intercepts, again, take a little bit more work. And this, to find the x-intercepts, we have to set the y value equal to 0, or the function g of x equal to 0. So we have x squared plus 9 equal to 0. Now we could factor this if we wanted to. We would factor this using imaginary numbers because this is a sum of two squares. But this is a little bit easier to use the square root property of equality. Just follow reverse order of operations. So let's go ahead and do that. So the first thing that I'm going to do here is I'm going to subtract 9 from both sides. When I subtract 9 from both sides, that's going to eliminate the 9 on the left side and gives me x squared equals a negative 9. Then I need to get rid of my square there by the x, and I can do that by square rooting both sides, taking the square root of both sides. Remember that when I take the square root in the process of solving, it's going to give me both a positive and a negative case. So I need to make sure that I put plus or minus out in front of my 9, or negative 9. So this is the plus or minus the square root of negative 9. Remember, if I take the square root of negative number, essentially what I'm getting into is I'm moving from the real numbers into imaginary numbers. So the square root of positive 9 we know is 3, and because the square root of negative 1 is I, my answer here would be plus or minus 3i. So what does this tell me about my x-intercepts? Well, this problem is actually a little bit different than the previous ones. The x-intercepts here, or my solutions, essentially what I'm finding is the solutions to the equation for x, are imaginary numbers. So what does imaginary numbers look like on a graph? Well, they don't show up. So this problem has no x-intercept. And we can see that graphically. So if I go over here to my graphing calculator and I show you x squared plus 9, and take a look at this graph, and I can see that it's opening up, and its initial point, the vertex, is above the x-axis, and it's just going to go up. I can zoom out here and see that it goes up forever and ever and ever, and it does not intersect with the x-axis. So there are cases where we don't have x-intercepts on a graph, and those are the cases where our x-intercepts, or our solutions to the equation, result in imaginary numbers. So how do we find, algebraically, how do we find the y-intercepts? We set x equal to 0 and then simplify, or just take the constants. How do we find the x-intercepts? We set the equation equal to 0 and we solve. Moving forward, we can use that same idea to actually write equations for quadratic equation, for quadratics, given the roots. Roots, you see this word root here in problem number 2, right? For each of the following, write the standard form of a quadratic equation with the given roots. Root is another word for solution, Okay? So we essentially have two solutions, and we need to write the equation. And we want to write it in standard form, which if we go back up here is ax squared plus bx plus c. So in order to do that, we use the concept that we get from factoring. We use essentially the zero product property. We're just going to use it a little bit differently. So because I have two roots, I have two solutions to my equation. So I know that x equals root 2i and x equals negative root 2i. Now what I'm going to do is go back up here to where we factored. I'm going to go back up to where we factored here and look at 1a. Here are my two solutions, my x-intercepts, -1 and +4. They came from factors x plus 1 and x minus 4. Essentially what we can do to get factors is to move these pieces that are equal to x to the same side as x, and that's a factor. So if I have x equals 1, I could add 1 to both sides, and I would get x plus 1 as a factor of the equation. If I added, or sorry, in this case, if I subtracted -4 or subtracted 4 from both sides, I'd get x minus 4, which is a factor of the equation. From there, we can create the equation just by multiplying those two factors together, and that's going to rewrite the equation in standard form. So basically what we saw here in 1a when we needed to find the x-intercepts is we factored and then we set the factors equal to 0 and we solved. So we solved for x. Now we know what x is. We're going to go in reverse and we're going to multiply to end up getting us back to the standard form of the equation. So let's go ahead and do that with problem 2a. So what I know again are my values for x are root 2i and negative root 2i. So let's call this function f of x. And if I have two solutions, those two solutions come from two factors. So the factors here are going to be x with something and x with something else. So what I would get to the solution of x equals root 2i, I would want that to be equal to 0, so I'd need to move that root 2i back to the other side. So I would end up subtracting a root 2i here on the left side. So my factor is x minus root 2i. On the right side, I would do the opposite. I would need to move this negative root 2i over to the left here to put it with x to create a factor. So I would add root 2i for that case. So again, we're trying to take that value that is equal to x and we're trying to move it on the same side as x so that now we have that factor. So my two factors are x minus root 2i and x plus root 2i. Now, if I want this equation in standard form, all I have to do is multiply and simplify. So I'm going to first distribute. So I'm going to take the first x over here in the left binomial, multiply it to x, which is x times x is x squared. I'm going to take x times a positive root 2i. So this is going to be positive root 2i times x. Okay, we can't really combine any of those together because we have a square root, we have an imaginary unit, and we have a variable. So we're just going to list them all together as multiplication. Now I'm going to distribute this negative root 2i. So I'm going to take negative root 2i times x. So what that would give me is minus root 2i x. Because again, I can't combine the root 2, the I, or the x. They're all different forms. I would also take this negative root 2i times that positive root 2i. So that's going to give me a negative. Root 2 times root 2, you can do that in your calculator if you need to, but root 2 times root 2 is root 4, which is 2. And then I times I gives us I squared, which we should remember is equal to -1. So now let's simplify this equation. So f of x is equal to, there's nothing to add or subtract with x squared. These two root 2i x's are opposites, and so they're going to subtract down to give you 0. And now I have -2i squared. Remember, I squared is -2. Sorry, I squared is -1. So -2 times a -1 is +2. So my answer, my final solution for this function is f of x that is equal to x squared plus 4. So x squared plus 4 is the equation for that given quadratic. So we can use this method to build equations for quadratic functions, given that we know their x-intercepts, their roots, their solutions, their zeros. All the same words for, or different words for the same thing. So a root is a solution, is an x-intercept, is a zero. Okay, all the same thing. So we're reversing that process of factoring. We're using those zeros to find factors, then multiplying, and now we have the standard form for the function. Let's go ahead and take a look at 2b. So now we know that the only x-intercept is -5. So the only solution is x equals 5. So let's call this function g of x. Let's use the same concept here with g of x. And we need to find a factor of g of x. Well, to find a factor, I need that -5 to move over with that x. So I'm going to add 5 to both sides. So when I do that, I get x plus 5. So my factor is x plus 5. This cannot be g of x. This is a quadratic equation. So let me go ahead and show you graphically. So if I had x plus 5 and that was it, I have a linear equation, and that's not what we're looking for. We're looking for a quadratic equation. What I know about roots is they can occur more than one time. The same root can occur more than once. So let me see if I take this and call it x plus 5 times x plus 5. What happens then? This is a quadratic equation. We can see that, and its only x-intercept is -5. So every quadratic equation is going to have two solutions, but that does not always mean that the solution is going to be two different places on the x-intercept. In this location, it touches the x-intercept and bounces off of that x-intercept, which we're going to talk about some details for that later on in the year, but it's a recurring solution of x equals -5. To get a quadratic equation, we already know that we have to have something that is x squared. And so in order to get an x squared but only have the x-intercept of -5, we need that factor x plus 5 to repeat, to show up twice. So we can write this as x plus 5 quantity squared, or x plus 5 times x plus 5. Now, if you remember, I did give you guys a shortcut for multiplying out binomials when they're squared. If you need to, you can write out x plus 5 times x plus 5 and you can distribute it. Let's make this a little bit faster. Remember that it is the square of the first term, so x squared, 2 times the two terms multiplied together, so 5x times 2, which would be 10x, and then the square of the last term, 25. So my function here is x squared. For g of x is x squared plus 10x plus 25. Now let me go ahead and take a look at that graphically. I'll take a look at my graphing calculator, and I graph. Here we have the graph that we already knew was x plus 5 squared, and I graph that as x squared plus 10x plus 25. I can see that here's my graph, this blue or purple color here, and it does have one x-intercept, and that is at -5. So after I get the standard form, I can go ahead and put that into my graphing calculator and check that to see if that matches up with the x-intercepts. Now, the reason I didn't do that in 2a was because our x-intercepts are imaginary, and so they're not going to show up on the graph. So we have to trust that we work through this one correctly using our algebra. So these are some algebraic steps that we can use to find the x and y-intercepts for a function, given that we know the function in standard form, and also write the standard form of a function, given that we know just the x-intercepts and the x-intercepts alone. If we needed to, from here, we could identify what y-intercepts were for this function. And this is a good place to stop part 1 of the notes. So tomorrow, or in the next video, what we'll do is we'll take a look at the vertex form of a function. and how we're going to graph the functions based on different forms, whether in their standard form or in vertex form. As always, thank you guys for tuning in. I'll see you soon.